This is question 1 in the multivariable regression modeling chapter 8 of the regression models textbook. The question asks us to load the dataset seatbelts as part of the datasets package via the command data seatbelts. And we're going to use as.dataframe to convert the object into a data frame. Then we're going to fit a linear model of driver deaths as the outcome with kilometers and petrol as predictors. And we're going to interpret our results. So we're going to do library, data sets, it's lowercase d, library data sets, and then data seatbelts with an uppercase S. Now let me just do lowercase seatbelts is equal to as.data.frame of seatbelts, because this, I think it's stored as a time series object or something like that. So now it's a data frame. Let's do head of seatbelts. So it's drivers killed, drivers front, rear. So I looked up the paper on which this was based. This is the number of drivers killed per month in Britain. This is the total number of drivers. The total number of driver accidents of any kind, and drivers killed is just specifically killed, where drivers is killed or seriously injured. Front of the car, rear of the car, where the killed driver was, or where the killed or seriously injured driver was sitting. Kilometers is a measure of total distance driven that month. Petrol price is, you might notice this clearly isn't in pounds. So this is actually, it's what they're calling real petrol price, which is the petrol price relative to some retail index, and then a measure of killed in vans, and then whether or not the seatbelt law was in effect. So in this analysis, we're just going to look at drivers killed, and we're only going to have two predictors, kilometers and petrol price. Okay, so if we wanted to fit that, we could do fit is LM. We want drivers killed. It's a morbid data set. Is kilometers plus petrol price. And then data equals seatbelts, my lowercase seatbelts, because that's the one I converted to a data frame. There's my fit. If I do summary of fit, let's just get the coefficient table. There we go. So there's a couple of problems with this right off the bat. There's the first thing is that the intercept is going to be interpreted as the expected number of drivers killed for the average for 0 kilometers driven and for a petrol price of 0. Again, that's not very meaningful, so the intercept isn't very meaningful. The other thing we're seeing is that the numbers are a little off, and that's because the intercept is at 10 squared order of magnitude, whereas the kilometers one is 10 to the minus 3, and the petrol price is 10 to the second. So if we do something like this, round our coefficients, we can see the numbers a little bit more clearly, but it still would be nice to interpret these numbers a little bit better. So we'd probably want to center kilometers, center petrol price, and maybe rescale both of them to a little bit more meaningful scale. Without that rescaling, then the kilometers is going to be interpreted as the impact of a 1 kilometer change. But if I do summary seat holding petrol price constant, seatbelt star kilometers, we see that it's in the tens of thousands for most of the range of the data. So 1 kilometer change in that variable isn't very useful. Petrol price, if we summarize petrol price, again, this isn't in units I understand terribly well, because is not pounds, it's in pounds. It's what they were calling real price. So pounds relative to some retail, some index. So these numbers, again, I'm not 100%, the units aren't terribly meaningful for me. So I'm going to load up dplyr, and for petrol price, because I'm not terribly well versed in the units, what I'm going to do is just standardize it. I'm going to subtract off the mean and divide by the standard deviation, and I'll create a variable called little pp that is just normalized petrol price. And then mm is just going to be the kilometers divided by 1,000. So I got that because that's a megameter. So that's 1,000 kilometers, and then I'm going to center that variable. I did that because I just thought a 1,000-kilometer increment seems pretty reasonable and easy to understand. Okay, so there we go. Now let's look at the head of our new seatbelt data set that dplyr helped us create, and there we see our new variables. Now let's try fitting our linear model where drivers killed is the outcome, and then we want our petrol price, our centered and rescaled petrol price, normalized petrol price as a predictor, and we want the centered 1,000-kilometer unit measure of distance in there as well. I forgot to tell it to look at my data frame seatbelts. Okay, summary of fit. Let's look at this. So now it has kind of more meaningful decimal places because it's not trying to calibrate between several different large changes in orders of magnitude. So the intercept 123 is the estimated number of drivers killed for the average petrol price and average distance driven. The petrol price of -7, or the petrol price coefficient of -7, means that we expect 7 fewer deaths, or we're estimating 7 fewer deaths per 1 standard deviation change in petrol price. Holding the miles, the kilometers constant. The MMC variable, remember, was 1,000-kilometer increments. So that is referring to about 2 fewer deaths for every additional 1,000 kilometers driven. Again, those are maybe a little bit counterintuitive, but they both kind of represent the same thing, suggesting maybe a lot more distance driven means fewer accidents. And so there's maybe ways you can interpret your way around that. That seems a little odd, but for the time being, let's just take this as if these were the estimates, and so those would be the interpretations.